Hello everybody, how are you doing? This is Professor Carlos Torres-Verdin broadcasting live from the beautiful hill country of Texas. It's raining. I hope you hear the thunder. No lightning, I'm safe here. But just wanted to show you the beauty of the landscape. When it rains, the clouds. There's a lot of chemistry going on here. There's a lot of electrochemistry. And that is very pertinent because today's lecture, Information Evaluation, Principles of Information Evaluation, PGE358, Spring 2020. Today we're going to talk about spontaneous electrical potential. That's an electrical system, an electrical measurement that we do in boreholes. And it's very, very interesting because it combines a lot of very different concepts having to do with electricity, with the chemistry, membrane potential, diffusion potential. It has a very interesting story with the Schlumberger brothers, Henri G. I'm going to talk about all of that. I hope you enjoy it. It's very nice and it's very lively. So let's go and let's do it. Hello everybody, how are you doing? Now we're going to start with the formal presentation. We are going to talk about the engineering and physics principles behind spontaneous potential log. We are going to describe the petrophysical applications that come from borehole spontaneous potential measurements, and we are going to use how these measurements are widely used to calculate the electrical resistivity of formation water. So it provides an alternative way to calculate electrical resistivity of formation water compared to the procedure that we have talked about before that has to do with electrical resistivity measurements. And I'm also going to talk about some of the limitations and corrections that need to be implemented to spontaneous potential logs before using them for any petrophysical activity. Okay, the material that I'm going to talk about here is can be found as part of the PowerPoint presentations that I describe here, and also the example that I'm going to cover, and I cover at the end, but I cover also within the text, is on pages 1 to 3 of the compendium part 2. Chapter 6 of the textbook has a very good description of all the topics and equations, and please I remind you that all of the equations that we're using in this presentation and also that will be used for the homework assignment in connection with this presentation can be found in great detail in the appendix of the textbook and also at the very end of the well-loved compendium part 1. So what happens? What is the origin of spontaneous potential log? It comes from the drilling process. When you drill a well, going through a siliciclastic sequence or any sequence for that matter, what happens is that one exposes or makes contact with the fluids in the formation. So the fluids that we have in the mud now become in contact with the fluids that we have in the formation. And that contact gives rise to electrochemical interactions, and those electrochemical interactions are going to produce phenomena that are reproducible and measurable. So when a when a well is born, what happens is we have the well, and then we drill the well with a type of mud. And the type of mud will come typically at a pressure that is higher than the formation pressure because we have an overbalanced well. And because of that, when we encounter porous and permeable formations, we will have the presence of mud filtrate invasion. And the invasion itself happens because we are having two fluids in contact. The spontaneous potential log will take place only in the case when the mud is water-based mud. It never happens when one has oil-based mud because of reasons that I'm going to cover in it. But essentially, we run the logging tools, let's say in open wireline mode, from the bottom up, several tools, and we plot the measurements. And one of those measurements is resistivity, some others are gamma ray, and spontaneous potential. Of course, we also have neutron density, all of the triple combo, quad combo, all of the measurements. But essentially, the point that I want to make is that the drilling process exposes the interaction between the fluids in the mud and the fluids in the formation. Now, here's another cartoon. We drill the well. The well comes with mud filtrate, and then we drop an electrode. And the electrode that is run from the bottom of the well up is grounded on the surface. Essentially what we have is an electrode that is run, and then we ground it on the surface. The connection where we ground it has to be quiet, electrically quiet. We don't want a situation where the electric fields near the grounded electrode might change over time because of a generator, because some other activity happened near the electrode will modify the measurements. We want the measurements to be reflecting only variations that happen in the borehole. So and what we do is when we measure the voltage difference between the electrode in the borehole and the electrode that is grounded at the surface. And here is the spontaneous potential log. It's an electrical potential measured in millivolts. It has a polarity, it could be plus or minus, and it has to be interpreted in combination with the gamma ray log. And why is that we measure an electrical potential? So it turns out that the reason why we measure an electrical potential is because there's an electric field developed inside the borehole. An electric field. And it's a spontaneous electric field. We don't produce it. It's just there to be harvested. And why is it there? It turns out that it's because of the interactions between the mud filtrate and the formation water when the well exposes the contact of the two fluids. Now, what are the facts? Here are some of the facts. It can only take place in the presence of water-based mud. No way that it will take place in oil-based muds. Why? Because we need to have electrolyte concentration in the mud. And oil-based mud does not allow electrolyte concentration. What is that? What is SP? It measures a DC electrical potential. Essentially, we have a time constant electric field being developed naturally, spontaneously in the borehole. And the values of that field produce voltages of millivolts. It can be positive or negative, like in any electric field, in any voltage. And it's there for us to harvest. It's spontaneous. We don't control the source. The only control is the presence of mud filtrate in contact with formation water. And it is formed when there's a difference in the electrolyte concentration between the mud and the formation water only. And when there's a difference in electrolyte mobility between the anions and cations that are parts of the electrolyte. The difference in mobility and the presence of a concentration gradient, the two of them are going to be responsible for the presence of this electric field inside the borehole that we measure with that moving electrode. And the most important thing is that it can be used to estimate the electrical resistivity of formation water. It just gives us an alternative way to estimate the electrical resistivity of formation water. And the attractive part of it is that we don't need to know what the porosity of the rock is. It doesn't depend on the porosity. And we don't need to know what Archie's parameters are to be able to calculate RW, which is the case when we do calculations of RW based on resistivity. But is this as reliable as a calculation of RW performed with electrical resistivity measurements? The answer is unfortunately not. And we'll see why the differences. So if you have a chance to calculate RW with resistivity measurements, it's better to do it that way than with calculation of spontaneous potential measurements. But if you do the calculations both ways and you find differences, those differences can expose certain rock properties and fluid properties that could be of interest for the formation evaluation analysis. Good. Now, this phenomenon is actually very easy to reproduce in the laboratory. Let me show you. You need an oscilloscope, you need some electrical cables, and this instrument that you see here, this borehole, this pipe is supposed to be the borehole, and the outer pipe is supposed to be the outer radius of the formations, and you can fill in any kind of property with water that you want. You can put small glass bead, large glass bead, presence or not presence of salty water, fresh water, hydrocarbon, and so forth, so on, and you can move the cable up and down, and with the oscilloscope measure the electric field, and your ground electrode can be placed at a location which is electrically stable. That's what we do. We can reproduce these measurements easily in the laboratory. Now, how do spontaneous potential logs look like? Here's an example of pages 1 to 3 of the compendium part 2. This is an example of Gulf of Mexico that I've been using repeatedly in these presentations. We have this track has spontaneous potential log. That's the red one. If I make a zoom on the units, that zoom will show precisely these values. Spontaneous potential runs can go from negative values to positive values, and is expressed in millivolts. So because it's an electrical potential, as I said before, it can have negatives or positives. The polarity is actually very important in this example. The other thing that I want to point out is that when we identify and measure the spontaneous potential logs, specifically for the calculation of RW, we always have to estimate what is called the shell baseline, which is the value of the spontaneous potential at places where we have a pure shell. That line becomes our reference, it's like our compass. And then what we do is we measure the deflection of the SP log with respect to the shell baseline. Could be to the left or to the right. If it's to the left, we call it negative. That's one example. Now, if you were to have in hypothetical world the same well, but in one case you have formation water fresh, like in this case fresh formation water, and here salty formation water, what will happen with the same type of mud is that if you have the shell baseline, which is the constant line across shells, and at the value of the spontaneous potential for a pure shell, that is a reference in both cases, and you will see that if formation water is saltier, higher electrolyte concentration than the mud filtrate, the deflection will be to the left. Whereas if the formation water is fresh, so we have more higher electrolyte concentration in the mud than in the formation, then the deflection will be to the right. And the reason we can do this because these are numerical simulations, but it's important to understand the differences because those are the things that we want to inspect in the analysis of spontaneous potential logs. And I want to emphasize that the shell baseline serves as reference, is our compass to do calculations and to understand the behavior of the spontaneous potential log. Here's an example in the field, saying two wells in the same field drilled with different muds. In one case, in the two cases, we have the same sandstone development intersected by different wells. But what we see here is that in one case, with respect to the shell baseline, the spontaneous potential is positive. whereas in the second case, with respect to the shell baseline, spontaneous potential is negative. Why? Because in one case, here, the salt concentration in the formation water is higher than the salt concentration in the mud. And the opposite is here. And why so? Because the drilling muds were different in the two wells. Both were water-based mud, but there's electrolyte concentration was different. So polarity is very important and reflects the differences in salt concentration between the mud and formation water. Now, why is that we have this spontaneous electric field, DC electric field in the borehole? Why does it happen? This is actually a very interesting question. So we have to understand what is the physics behind. And the reason is, there are two reasons. One is that we have a concentration gradient, an electrolyte concentration gradient between the mud and formation water. That's one. And second, because for electrochemical reasons, the mobility between the anions and cations that we have in formation water is not the same. We have differential mobility. So those two factors are going to give rise to the electric field, the static electric field, spontaneous electric field that we have in the borehole for us to harvest. That's what we do. We don't have to impose a field. The field takes place because of these conditions. Here's an example of why gradients in concentration are important. This is a picture of the Amazon River in Manaus, Brazil. This is where the Amazon River is formed by the confluence of two rivers. One is coming from Peru and the other one is coming from Brazil. But what you can see the differences in color. And why do we have differences in color? Because we have differences in concentration of dissolved solids or even electrolytes. But so when this concentration gradient happens, then immediately we have thickened diffusion. So the solids and the ions with these so different concentrations will tend to equilibrate, and the equilibration takes place according to a thickened diffusion process. Here is a plan view of the same process. We can see how the front is changing in concentration and how this front has the manifestation of a diffusion process. Of course, when the rivers are moving, it's not only diffusion, we have the superposition of advection and diffusion process. But this is a very interesting natural example of how concentration gradients will give rise to mobility and diffusion of the ions toward equilibrium. But something like this happens in the borehole. Let me just explain what happens in the borehole. In the borehole, when we drill the well, right here is the well, we have a certain concentration of sodium chloride. That concentration gets exposed with the concentration of sodium chloride in the sandstones that we have right here and also in the shales. So now we have a concentration gradient. It could be one way or the other, depending on where the concentration is higher. But so now the ions are going to tend to equilibrium. And the equilibrium is going to follow a diffusion process. But here's the thing. When they do the diffusion, we are going to have something interesting, that because the diffusion takes place through this porous medium, which is the sandstone, there will be differential mobility between the anions and cations. That differential mobility will selectively discriminate one of the two, the anions or cations, and so that they will move more of one than the other. The second component that happens is here, when the sandstone over here is or has a concentration that is different from that of mud, filtrate, an intervening shell like this one can be used as the contact between the two substances. And that shell will also offer a path for the mobility of the ions toward their equilibrium. But it turns out that shales are very interesting because when they offer that path for equilibrium to the ions, they act in a very discriminatory way, in the sense that they favor the passage of the cations much more than the passage of the cations. In fact, most of them work as what is called a semi-permeable membrane that only allow the passage of one of the ions, in this case the cations. And so when that happens, the concentration gradient and the fact that we have differential mobility because of membrane or because of diffusion, then more of one ion is going to reside in the borehole, and the differences and the excess of electric charge is going to be responsible for the presence of the electric field that we measure with the electrode. And if we make those measurements relative to the electric field at the shales, then the remaining portion of the electric field will be the spontaneous potential. And that's what we typically measure across these rocks. So two things: a concentration gradient, electrolyte concentration gradient, and second, when the ions trying to equilibrate, the process of diffusion is going to favor one of the ions more than the other, effectively separating the charges, and that separation of charge will create an electric field. And that's the origin of the spontaneous potential law. Now, brief historical perspective. Who invented spontaneous potential measurements? Two things: clever people, lots of serendipity, and lots of creativity. And the story goes back to the Schlumberger brothers, Conrad and Marcel Schlumberger. Very interesting people. We can spend a whole lecture on them, but I don't have time. Suffice it to say, to tell you that for a very long time, the Schlumberger brothers were interested in doing surface measurements of electrical resistivity, because they knew that the electrical resistivity of the ground, of the subsurface, will tell them what kinds of materials the subsurface will have. And for instance, they could have water, they could have dry material, they could have mineral deposits, metals. So if they were able to measure these variations of electrical resistivity of the ground over a large surface area, maybe they could detect variations in the ground composition. And those variations, they could be used to ascertain presence of interesting subsurface materials. So they came up with this idea that to measure the electrical resistivity of the ground, they will have two electrodes, A and B, that will inject electrical current with a current source. And so they will know what the electrical current is or was that was injected. Now, to measure the electrical resistivity of the ground, they also needed to measure the voltage measurements. And they came up with this idea that it could be measured not with the same electrodes that they are injecting the current, but with an additional separate set of electrodes that they call M and N. And those M and N electrodes will be separated between them and from the electrodes A and B, and they were able to calculate what the electrical resistivity of the ground will be by knowing the current measured with A and B and measuring in from the voltage between M and N, taking into account geometrical conditions and also taking into account the average properties of the soil. And with that, they went on and generated this measurement. They actually developed the technology, all the circuits, the analog circuits, the measurement systems, and as shown here, they produce this electrical potentiometer. Here is Conrad Schlumberger taking measurements in 1912, and he was using some sort of an audio transformation of the signal, and by mapping these differences, they could measure them and plot them on the ground. And here we have Conrad again in 1920 in one of his properties, these family properties, making measurements with this potentiometer. And then here's another beautiful photograph on Saint-Louis, Les Mines en France by Conrad Schlumberger making the same measurements. And this was at a site very close to an ore mine, in an iron mine for that matter. And when he completed those measurements, he plotted them. Here is a plot. And these are the contour lines of those measurements. And he found that there was a local maximum of electrical conductivity right here. And it turned out that that local maximum was because at that point in the subsurface, there was a considerable deposit of iron. So this was a eureka moment that Conrad Schlumberger in 1920 was able to use his surface electrical conduction measurements to detect presence of ore deposits in the subsurface. So no longer now you had to dig and find. Now you can just measure on the surface, and from the measurements of electrical resistivity you could detect where potentially one could have good deposits. Now, the interesting thing that happened afterwards is this. There were oil fields nearby, and in the oil fields people needed to find out what was there presence or not presence of oil. And in some moment that is not clearly understood, the Schlumberger brothers came up with this ingenious, fantastic, and transcendental idea that the electrical resistivity measurements that they were doing on the surface could also be done in depth. And they designed this measurement system in which there were electrodes, injection electrodes A and injection electrode B on the surface. And they had two voltage measurements points, M and N. This is the principle of what we now call lateral log. Of course, it was very easy to design and adapt. But when they adapted, they came with many, many problems. It was not the same thing as doing the measurements in the ground, on the surface. It was not as easy. So it took a long, long time before they were able to adapt this measurement. And for the adaptation of this measurement, they hired a super intelligent person. And what happened, the reason why this was important is because there were many oil fields nearby. Hildebrand was one of them, 1925. And they were detecting properties of rocks just by looking at cuttings or whole core, and that was very expensive. So they came up, I really don't know how this happened. I've asked many people about this, but I don't know where this or how this eureka moment came when they transported the idea of surface electrical conductivity measurements to wells. But they hired a very intelligent, creative, and bright mind, Henri G, a prodigy. This person invented so many of the most important well logs, borehole measurements that we continue to use today. And so he was hired, and he was commissioned to develop in the system in the borehole that would make this idea from the Schlumberger brothers a reality. And he did. So much so that actually in 1927, this is the first well log acquired by plotting electrical resistivity measurements in a field called Hildebrand that I showed before. And here you can see values of high electrical resistivity correlated with presence of hydrocarbon or with layers of low porosity. So they knew that now electrical resistivity could correlate with presence or not presence of hydrocarbon. And this was actually a very interesting idea, and that's the origin of Schlumberger. Of course, after that, many bright people worked trying to understand why the electrical resistivity was high in the presence of hydrocarbons, and it took a long time before Archie came along and explained this whole theory. But that's the beginning. And now, what happened? What happened was this, is by serendipity, someday they were looking at these electrical resistivity measurements in the borehole, injecting the current, and they stopped injecting the current, and they kept on measuring electrical potential. So they said, how can we measure electrical potential when the source of the current is gone? So why are we getting? And for a long time, they thought that the measurement was noise, that it was electronic, it was something else, and they racked their brains and thought different things, troubleshot everything possible, and it took this super bright, ingenious mind, Henri G, to understand that that measurement was not noise. It was a natural measurement that obeyed physical principles. And he, in combination with the Schlumberger brothers, were able to come up with a theory as to why those potentials were not only natural, they were not noise, but also could be harvested for information about the ground. And some of the seminal papers on spontaneous potential belong to Henri G, and those papers continue to be cited extensively. So here is what happened. Here is a measurement made in 1927 where we have the electrical resistivity log. That's what they said to do. And then here we have the spontaneous potential log, which is acquired just by turning off the source of electrical current and measuring the electrical potential between an electrode in the borehole and an electrode in the ground. And then they saw correlations. And initially they thought that this was an idea because they found that the presence of deflections of the SP would correlate with permeable beds. So at the beginning they were touting this technique as a way to detect permeable beds. So it took a long time before they understood why this was happening. But that's the origin. That's how it came about, by serendipity and a lot of creativity and lots of brain power and intelligence and physics. So what are the applications of spontaneous potential log? The first and foremost is for the estimation of electrical resistivity for measuring water. It's an alternative technique compared to doing that with electrical resistivity measurements. It can actually define where one has permeable rocks compared to impermeable rocks in a qualitative way. It allows the detection of boundaries. It also can indicate qualitatively the degree of shaliness of a permeable rock. Also qualitatively that there is hydrocarbon. Is widely used in geohydrology for assessment and evaluation of aquifers. Quality water, widely used. And there's another component of SP which we call streaming spontaneous potential that finds a lot of applications in civil engineering, for instance. So there's a lot that has occurred with this measurement. But how does it work? I mentioned before that the physics, this is the brain power idea that came up with from the Henri G and Schlumberger brothers, is that they realized that this was due to two things. The electrolyte gradient between mud filtrate and formation water, and more important, the differential mobility of anions and cations in solution in water. How does it work? Let me just give you a free explanation here. Very simple. Let's say that you have two substances with different ion concentration. Here you have a high concentration and here you have a low concentration. And you put them in contact. So immediately we will have the tendency toward equilibrium from high concentration to low. That's a gradient. And that gradient is realized by this logarithm here. But then a famous German scientist, his name is last name is Nernst. He realized that when that happens, that the free diffusion is not equal for the anions and cations. We have differential mobility, and he used these so-called transport numbers. So there will be a transport number for the cation and a transport number for the anion. If they have the same transport numbers, this quantity becomes zero, and therefore an electrical potential does not develop. But if there's a difference in the transport numbers of the cation and ion, then he found that difference could give rise to an electrical potential. And that idea was the basis of the studies conducted by Henri G, that he realized that this could be the origin. Now, we know that when you have free diffusion, there's a difference between the transport numbers of the cations and ions. But there's another physics situation that could happen. And that physics situation is what we refer to as a semi-permeable membrane. When you have a restricted diffusion in space, so you make you make the transition from the high concentration to the low concentration. You have the gradient, you are formed to force the equilibrium. That's the gradient forces the equilibrium, the ion movement. But if you force the equilibrium through a constriction, then, and if you design this constriction such that only one of the two, in this case the cation, has mobility, then essentially you can design it so that the transfer number of the anion is 0 in this equation. So if it's 0, you only have one transport, and it becomes a very simple relationship. So now you can actually, if you have a semi-permeable membrane that only favors the passage of one of the two, in this case the cation, then that will produce a concentration of electric charge, no longer equal pluses and equal minuses. You will have more of one sign on one side than the other, and that difference in electrical charge will give rise to an electrical potential. And that electrical potential is the one that we measure. And the idea is that if you measure the electrical potential that results from this separation of cations from anions, then indirectly we can estimate the original concentrations. That was the idea behind this. Now, just to remind you, when we talk about anions and cations, cations in the case of sodium, anions in the case of chlorine, these are hydrated ions. In the case of hydrated with in hydration, they actually have 6 molecules surrounding them, 6 molecules of water. So when I talk about these anions and cations, I'm actually talking about not only themselves, chlorine and sodium, or sodium and chlorine, but carrying these 6 molecules of water with them. That's the way they are formed, they are encountered in solution. Now, when we have this situation, something interesting happens. In the case of sandstones or limestones, anything that has a sufficiently large throat size, when we try to equilibrate the differences in concentration, we found that the transport numbers of chlorine and sodium, for instance, there could be many other electrolytes, but let's try to normalize the discussion for a very common electrolyte, which is sodium chloride. What we find is that the transport numbers of sodium and chlorine are about a difference of a factor of 2. Not quite, but see here is 0.4 and 0.61. Because of that, there's a slightly higher mobility for chlorine compared to sodium. And that difference is sufficient to separate the pluses from the minuses through the throats. And because of that, in the end, we will end up with more of the positive charge on one side and more of the negative charge on the other side. And that will give rise to the electrical potential. So that difference in transport numbers. Now, what happens if we decrease the throat size like in the case of a shell? Well, it turns out that when you do that in shells, the transport numbers between the two become much more different. In this case, the chlorine is 0.1, close to 0, compared to sodium, which is 0.9, close to 1. For all practical purposes, although that's not the case, we could assume that, for instance, the chlorine transport number is 0, and then shells will become a perfect semi-permeable membrane, only allowing the passage of one type of ion. They are extremely discriminatory. They have a discriminatory behavior because they only let one type of ion go through. And because of that, the development of potential is much higher than in the case of just sandstones and limestones, just because the difference in ion mobility transport numbers is larger in the case of shells and sandstones. And why is that? The reason why shells have that behavior is because of the effect of electrical double layers. We also have electrical double layers in sandstones and limestone, but the effect of electrical double layers is emphasized when the constriction, the throat size, decreases. let me explain why this is the situation. But before I explain the electrical double layer, let me tell you what the diffusion potential happens. Here is, suppose that you have two substances with different concentrations. More concentration on the left, lower concentration on the right. If you were to place these substances in contact, then things will tend to equilibrium from high concentration to low. But if we force them to go through porous medium, in other words, we force this equilibration process to take place through porous medium, then we know that one of the ions will have higher mobility than the other. Consequently, the one that has more mobility in this case is chlorine. Sodium is also going, but the one that has more mobility because it has a higher transport number will tend to go more than sodium. Consequently, in this process, we are going to end up with much more negative electric charge on the right than on the left. And consequently, that difference in charge will cause, that separation in charge will cause an electrical potential. And now this electrical potential you can plug into your iPhone, to your computer, and power up. This is one way in which these potentials are formed. All right. Now, what about the electrical double layer? Remember, when we talk about shaly sands, I mentioned that surface to volume was important, that most of these minerals had an electric charge, a surface electric charge, and because of that, in the polarity of water, we will develop these thin films. But in addition to the thin films, now something else is going to happen. That if this negative electric charge is sufficiently large, it will begin to attract the cations to them. The attraction of the cations will cause a cloud of cations and will cause the volumetric concentration of cations to be very large in the vicinity of this. Of course, the attraction will depend on several things. But if you have clays have a very high surface to volume ratio and they have a very high negative surface electric charge. So the attraction of the cations is potentially very large. And that attraction causes a cloud. It generates a cloud of cations surrounding the clay minerals. This excess of cation concentration in the vicinity of charges is what makes up this electrical double layer, because we have a concentration of negative electric charge on the solids adjacent to a concentration of positive electric charge. That's the definition of electrical double layer. And the volumetric concentration of cations decreases as we walk away from the surface of the clay minerals. If we walk away far enough away, we will find that the concentration of cations and anions will equilibrate, like we do in bulk water. But near the clay minerals, it will be dominated by the concentrations of cations. This is interesting because if you were to force an electrical current through this medium, the electrical current will separate into two paths. One path going through the electrolyte. That's what Archie does. It forces electrical current to go through the electrolyte. But when you have these abnormally high concentration of cations near the clay crystals, some of the electrical current will tend to go through those clouds because it's more efficient. And that's the reason why Archie's equation doesn't work in the presence of grain-coating clay, because of this alternative path of conduction. So we have to correct for that if we want to render Archie's equation possible. So electrical double layer, that's the important thing that I want you to understand in shales. And that's going to be the reason why shales act as a semi-permeable membrane that is or given dominance to the passage of positive electric charge. Now, if I do another diagram of the electrical double layer, which is what I want to show here, is that electrical double layer, this is the surface. We have the hydrated layer that I've talked about before, the thin films, and then we have the abnormally high concentration of cations. And if we walk away sufficiently far away, then we go back to the equilibrium of equal pluses and minuses. Here, this picture is is a cross section across this boundary, where we have the negative electric charge, then we have the absorbed cations, and then we have the cloud of cations, and this abnormally high concentration of cations will cause an electric field. An electric field will be referred to as the zeta potential, but eventually we walk away far enough away, we will have equal pluses and minuses, and we will go back to equilibrium conditions. Okay, now what happens in the presence of clays? This is just to emphasize the same idea. Clays have a negative electric charge, so when we place them in water, we will have the hydrated layer, the thin films, because of the polarity of water, but we will also have an attraction of the cations, and the cloud of cations will be highly concentrated near the clay crystals, and it will begin to diffuse and disperse into the bulk medium. And this essentially creates the double layer creates an alternative path for electrical conduction of currents when enforced in rocks. Now, let me show you in more specific detail how this works for the case of membrane potential. So once again, let's consider that we have an aqueous substance with sodium chloride here with high concentration, and another aqueous solution with less sodium chloride, lower concentration. So now we're going to expose them, we're going to make them place in contact, but we're going to force them to equilibrate from high concentration to low concentration through a medium that is abundant of clays. What's going to happen is this: because of the negative electric charge and the cations that form on the cloud, then when there's an equilibrium condition, essentially that equilibrium condition and that presence of that electrical double layer would only favor the passage or the movement of the cations which are compatible with the cloud that forms in the electrical double layer. So in consequence, the clay minerals will favor the passage of cations more than the passage of anions, and that difference will promote a separation of charge, more plus positive charge on one side than the other one. And here comes the voltage difference that we need to generate that electric field. Here is the origin of the membrane potential. This technique, this procedure, this physics is widely used in for instance, in the manufacturing of batteries. Battery technology uses membrane potentials, membrane technology to separate anions from cations, and that separation causes the electric field. And same for filters, water filters. This technology is also widely used for that purpose. Now, when we return to the borehole, this is what happens. Now, just to remind you, we have the borehole, we have a certain concentration of sodium chloride, and now that higher or lower concentration is going to be in contact with the higher or lower concentration of sodium chloride that we have in porous media. And when that difference in concentration happens, now we have a way to equilibrate. The equilibration can go directly between the porous medium into the borehole here, directly, or it could be done indirectly by way of the shales. So we have these two alternative paths: equilibration through the porous medium itself between the mud filtrate and the porous sandstone, or equilibration between the sandstone and the mud filtrate through the shale. And what happens is that the equilibration that takes place through the porous medium is going to be governed by the diffusion potential. And the equilibration that takes place through the shales will be governed by the membrane potential. So in consequence, the spontaneous potential that we measure is going to be the result of the electric field generated by the separation of charge by the two phenomena, the membrane potential through the shells or the diffusion potential. And if we reference that to the membrane potential, then we will sense this difference, that electric field. And which one is more dominant? Well, it then turns out, as we indicated before, that the membrane potential has a larger difference between the transport numbers of the anion and cation. So that tends to generate a larger separation of charge than the diffusion potential. But that's the origin of the spontaneous potential, the superposition of the membrane potential and the diffusion potential. That's what we measure in the borehole. Isn't that interesting? It took a long time to come up with this explanation, but as you know, now it is an electrochemical explanation. It's not noise, and it's an electric field that we can use to harvest information, petrophysical information. And here is the summary of the two. So in the diffusion potential part of the equation, which is here, and here is the membrane potential part of the equation. The diffusion potential includes the differences in mobility between sodium and chlorine. You can see that the mobility of chlorine is higher than the mobility of sodium, and that's what comes into effect here. The logarithm of the ratio between the concentration of electrolyte concentration in the formation water with respect to the electrolyte concentration of mud filtrate is a way to express the gradient, the concentration gradient. And the constant, this constant is based on temperature, is based on ideal gases constants and Faraday's constant, but it's also based on the differences in mobilities. And when mobilities between sodium and chlorine are involved, then the constant gives rise to a value of 11.6 when the result is given in millivolts. Now, for the case of membrane potential, the mobility of one of them is 0.1 and the other one is 0.8. So if you take those into account and you take the difference between 60.7 and 45, with their respective 0.9 and 0.1, then you end up with this value of 59.1. So if you sum the two, we come up with a value close to 71. And that's how this value comes into perspective here. So in consequence, the measurement that we do when we subtract the potential measured across shells, that difference will be given by the logarithm base 10 of the ratio between the electrolyte concentration of water and the electrolyte concentration in mud filtrate. And we have a constant. So if we know the electrolyte concentration, sodium chloride concentration in the mud filtrate, and we measure the static SP, we can solve this equation for CW. And once we solve the CW, we can convert the CW into RW, and that's how we estimate RW. That's the process that we are about to show in more detail. And here is just the summary of everything that I said. The equation that governs the implementation of the algorithm for estimation of resistivity of formation water is based on the differences between the transport numbers of sodium and chlorine, and the ratio of the resistivities, or the ratio of the concentration, is a consequence of the concentration gradient. So we have a constant here that is truly a constant, minus 71, or in more general terms, we could modify this with the values that the transport numbers have for each one of the species. In a case where you have multiple electrolytes, ions, you could have potassium, chlorine, sodium, sulfates, nitrates. The idea is that you could include the transport numbers here, but typically what we do in the field is that we normalize it as though they were a combination of sodium and chloride. So we we calculate the equivalence between the transport numbers of those species to those of sodium and chlorine, and then that normalization carries on a multiplicative factor or a superposition effect, and so that factor is applied in the equations. All right. So in consequence, this is the situation we have in the field. So if you have a shell here and you have a sandstone, porous and permeable, when we drop the electrode connected through a ground stake, then this electrode measures an electric field that is naturally developed, spontaneously developed in the borehole. And that electric field is due to the superposition of membrane and diffusion potentials. Now, if the concentration gradient, the electrolyte concentration gradient between the mud and the formation is zero, there's no gradient, then the measurement will be zero. There's no concentration gradient, there's no movement of ions. As soon as we have a concentration gradient, then there will be a movement of ions and there will be discriminatory behavior, if you will. One of the ions will move more freely than the other. So here's what happens. If, based on that formula that we discussed, if there's higher concentration of sodium chloride in the formation than in the mud, then the deflection will be negative. So we will have a negative deflection. And if we have more sodium chloride, the concentration of sodium chloride is higher in the mud than in formation water, then that will cause a positive deflection of the SP. So the polarity of the deflection is an indication of where we have higher concentration of sodium chloride. If the concentration is higher in the formation water, then we have a negative deflection. And if the concentration is higher in mud filtrate, then we have a positive. So those are important elements to take into account. And that difference between the shell baseline, we measure the spontaneous potential across the line. In both cases, we measure the discrepancy with its sign, we call it SSP. And that difference with respect to the shell baseline is what we plug into this equation. And if we know the electrolyte or the sodium chloride concentration of mud filtrate, which we can measure at the surface, then we can solve this equation to estimate CW. And you can see that this equation does not care about porosity, does it? No, absolutely not. It only cares about the differences in concentration of sodium chloride electrolyte in formation water with respect to mud filtrate. And that is the equation that we widely use for spontaneous potential measurements calculation of RW. Now, if you ask me which one is more reliable, I can tell you that in practice, the procedure of calculating RW with electrical resistivity measurements is much more reliable, because in the case of spontaneous potential measurements, many things can happen. You can have presence of shell, you can have minor presence of hydrocarbons, you can have other factors such as variability of ions and cations, and all of those conditions, including invasion, will modify the value of SSP, and as a consequence, those modifications will create errors in the calculation of RW. However, if we have the calculations both ways and we have differences, and if those differences are larger than expected, then the differences can be used to indirectly ascertain important properties, petrophysical properties, or those water saturated sandstones. For instance, presence or not presence of shale. Now, when we measure the static SP with respect to the baseline, that's the shell baseline, it's important that we take this measurement first of all, in a permeable sandstone bed that is water saturated, that doesn't have presence of clay or shale. That in a situation where the bed thickness is sufficiently large so that the value is not suppressed by bed thickness, we also need to make the measurement in the center of the bed, right here, away from bed boundaries, eliminate shoulder bed effects. And also we want to make sure that there are no hydrocarbons. There could be several factors, conditions that could cause the value itself to be suppressed compared to the value that we have of that same permeable bed under ideal conditions. And the other factor is borehole size. If the borehole diameter is very large, then if the measurement is done at the center, then the distance from the borehole wall and therefore from the charge could also decrease the value of electric field. So these are some of the conditions that we need to take into account when we measure the static spontaneous potential. And so here's a summary that bed thickness is a significant concern. Presence of invasion is also a very important concern, because when one has invasion, the concentration front moves inside the formation, and as a consequence, the distance from the charge boundary to the borehole surface or the location of the electrode increases, and that also decreases the amplitude of the voltage. And avoid hydrocarbon saturation, and also we want to make sure that we make the measurements in the center of the bed. As an example, here's an example of something that we talked about before, one of the examples, where we have a bed that is partially hydrocarbon saturated and partially hydrocarbon saturated at the top and water at the bottom. We also see that the bed has intralayers of shale that limit the or place restrictions on what place to locate the baseline. The shale baseline is here, or it could be there, but it's also very important to make sure that the thickness itself in this example is not a problem. We have 6,600 to 6,660 feet, but we do see presence of hydrocarbon, and we also see presence of laminations of shale. So when we take the reading, we have to be aware of unfavorable conditions that could bias the calculation of electrical resistivity of formation water. Now, what are the most common environmental or geometrical conditions that need to be corrected before interpreting speed logs? Let me show you as an example this outgroup that we have shown before. So layer thickness is 1. Second is presence or not presence of shale, and other conditions such as presence of invasion also will modify the measurement. Essentially, they will suppress the measurement so that ideal is not properly is not in its proper condition for the calculation of resistivity of formation water. Now, as a summary, here's an interesting slide that shows it's a synthetic model that has the gamma ray log, the spontaneous potential log. We have the neutron and density logs in sense and processing units, and we have the electrical resistivity logs. Deep sensing is the red, shallow sensing is the blue. These logs were calculated in the presence of invasion. These diagrams over here, they're radial cross sections of water saturation, salinity, and electrical resistivity. And here we have the dominant logs, which are the gamma ray log in green, and spontaneous potential log in red. What we see in this area is that the layer thickness suppresses the value of the spontaneous potential, so we have to be mindful of that. Also, the variability of gamma ray, more or less gamma ray, also presence of shale will modify the value of the spontaneous potential log. Obviously, we would choose this line here as the shale baseline. and the deflections will be to the left. So that means that we have more salt concentration in the formation water than we have in mud filtrate. And there are also some conditions, for instance, over here where we have a certain amount of hydrocarbon, and that also modifies the values of SP. And in the lower section of the well, we also have a suppression of the SP, and that is due to the presence of shale base or non-negligible shale because of the values of gamma ray log. So, and of course, the presence of invasion also will suppress the spontaneous potential log. So when we go across a field study, it's important to take into account all of these variables that could affect the spontaneous potential log, so that when we decide where to take the reading to calculate our W, where we minimize all of those effects. Now, so those the summary is that you want to be in a bed which is sufficiently thick. You want to be in a bed which presence of clay or shale is negligible. Presence of hydrocarbon saturation is negligible. So we maximize the presence of formation water, and we also minimize the presence of invasion as much as possible. So here is a field example where we have the SP log in red and the gamma ray log in green. Extreme variability in gamma ray log. We also see that with respect to the shell baseline, the maximum amplitudes of or deflection of the SP take place at the bottom. And we observe also certain correlation, repetition of patterns in the resistivity log. We also observe the average values of porosity in this siliciclastic formation. The important thing to remember is that some of these suppressions of the spontaneous potential log are going to be because of the volumetric concentration of shell as indicated by the gamma ray log. So what we have to do is to select places where we have the maximum development of deflection with respect to the baseline, and in this case it happens to be at the bottom. If we do some simulation or do a simplified model a synthetic model based on the field case, we plot two conditions. We can do this when you do numerical models. We can have one spontaneous potential or resistivity for the case of 100% water saturation. That's the blue one here, shown here. Or we can have a case of partial hydrocarbon saturation, and that's the red one. And we also can have a situation with invasion. The important thing here is the following. Obviously, we see effects due to partial hydrocarbon saturation on the SP, and we also see effects due to laminations of shale. So it's important to remember how the different conditions and different effects are going to affect the spontaneous potential log, so that when we take the reading, we take it at a place where those effects are minimized. Now, another potential effect that we see very often in field logs is the characteristic drift of the spontaneous potential logs with depth. This is depth. And typically, or most commonly, this drift is due to increase of temperature. So the plot that you see here is over a wide depth range, so that the variations of temperature are significant. And second, another condition that often happens is that the properties of the shells are not constant over depth, and that also causes certain shifts. So what we do when we observe these drifts is that we correct for them. Essentially what we do is we flattened the drift line base for the shells, we flatten it, and then we modify all of the logs to be all the differences, so they are measured with respect to the flat behavior. This is a very common correction that is applied to SP logs that are acquired over a very long depth range and is necessary for calculation of RW. In geohydrology, the spontaneous potential log is widely used to appraise the quality of aquifers, more specifically to appraise the quality of the water. Of course, we want to, depending on the application, the uses of the water in the aquifers, we would like the water often to be fresh and drinkable. And the SP log in combination with the gamma ray log and also with the resistivity logs is an extremely valuable combination to for complementing and understanding the properties of these of the aquifers. And it's also very important to remember that in most cases in geohydrology, very few times they acquire the porosity, the neutron and density porosity logs. Very seldom do they do that. So because of that, the spontaneous potential log is an extremely good complement to calculate RW, because calculating RW from the resistivity log is next to impossible if we don't have an indication of the porosity. The other thing that is very important is that in geohydrology, the usage of the spontaneous potential log is very important for assessing ion mobility, and when in places where ion mobility correlates with permeability, obviously this is an indirect indication of permeability. One case in point is in the presence of fractures. Very often fractures enhance ion mobility, and very often that ion mobility is expressed in some way in the spontaneous potential log. So that's another very useful application of the spontaneous potential logs to assess quality of water in aquifers. Now, very often the question is made as to whether SP logs are sensitive to rock permeability. And the answer is sometimes, if ion mobility correlates with permeability. Let me explain, and that's not always the case, but usually what we have to do is we have to have different segments over a given log or depth section where we observe sufficient differences in the deflection of the SP compared to the shell baseline. And typically that will be a function of many things. Let's say that this is your shell baseline, and then based on this log we see variations, or based on this outcrop we might see variations of this kind, and maybe variations of this kind, and maybe variations of this kind. That usually happens not only because of bed thickness. Of course, when we compare SP variations, this will be the shell baseline of the SP, and the SP will be deflecting to the left here, indicating a negative. So if we look at these things from the viewpoint of bed thickness and realize that these variations are not due to bed thickness, or that the variations are not due to the presence of clay, then certainly what happens is this, that when you have impermeable rocks, they tend to behave similar to what happens in a shell. So you have ion mobility, and that suppresses the deflection with respect to the shell baseline, because those rocks tend to look more like a shell. But when you have full development of the spontaneous potential here, for instance, you can have a rock that has good porosity but not at good permeability and develop the same deflection, not because it has better permeability. So the discrepancy, sometimes you can actually assess differences in, or qualitatively know that a rock is less or more permeable than a reference rock just because the deflection of the SP is closer to that of the shell baseline. But when things have good porosity and good permeability, typically it's hard to observe differences between the spontaneous potential log, because as I told you, the spontaneous potential log is insensitive to porosity. So in the measure that we have presence of shell or reduction in the throat sizes, maybe yes, we can have a correlation between permeability and SP logs, but not usually. That's not the case. Now, what happens in carbonate rocks? In carbonate rocks, because of the, like in this example, because of the absence of shale layers or dominant shale layers, essentially the membrane potential due to shales as component of the SP is negligible. So the only component of the spontaneous potential that we have here in the absence of shale layers is due to diffusion. And when you have diffusion, the difference in transport numbers between sodium and chlorine is not very large. So in consequence, when we observe SP anomalies, SP logs across carbonate rocks that are shale-free, then we don't see very large variations of the deflection. In fact, it's almost impossible to find a shale baseline to have a reference, and seconds, the oscillations with respect to that particular reference line are very small, sometimes negligible. That's the reason why oftentimes the SP log is not valuable in the presence of carbonates. However, there are some carbonates that are close to the form close to the shoreline where you have some combinations with shales. In those cases, well, yes, you may have shale layers that could function as membrane potential, and therefore the SP could develop a larger deflection with respect to the baseline. We have also seen examples in volcanic rocks, especially in the presence of fractures, where ion mobility is increases in the presence of fractures, and that ion mobility or discrepancy between the mobilities of sodium and chlorine, anion and cation, is manifested in the presence of fractures. And that's one common, it could be one common application for detection of fractures, just along with the SP, especially in aquifers. Of course, if you have the complete suite of logs, you can assess the presence of fractures in a different way. Now, to calculate RW from SP measurements, we have to follow a very simple path. Notice that we're never going to use porosity here. The path is very simple. First of all, and we're going to have an example of this. First of all, we need to define the shale baseline, paramount. The location of the shale baseline, the value of the SP of the shale baseline is very important because all the calculations are based on that. Then we have to locate the best possible sandstone or rock that has the best conditions for calculation of RW. That's minimize the presence of shale, number one. Second, maximize the thickness of the sandstone. Minimize in as much as possible the effect of invasion. Minimize the presence of hydrocarbon. Make corrections for borehole size if necessary. All of that will give us a good place for location of the place where we want to record and take note of the SP of the sensor. After doing that, then we calculate the static SP, which is the difference between the SP at the sandstone and the SP at the shale. Sign here is very important, so we have to keep track of the sign, plus or minus. Then the next step is we go to look at the header. From the header of the log, we read the resistivity of the mud filtrate and the corresponding temperature at which this measurement was made at the surface. And using the formula that we have in the appendix, we transform the resistivity value and the temperature at which this measurement was made into concentration. It's very important that we normalize these concentrations, so these are equivalent concentrations of sodium chloride, because that's our normalizing ion cation species. And then we use the equation by Nernst and solve it for CW, and which is about the concentration of sodium chloride equivalent in formation water, and for that we multiply the concentration of sodium chloride equivalent for mud filtrate, and the SSP is a previous value that we had from the difference between the measurement and the shale baseline. Then from that CW, we take that measurement and calculate the corresponding formation temperature, and with the two concentration of sodium chloride equivalent and temperature, we calculate the corresponding RW. So I want to emphasize that nowhere in this procedure we had the need to calculate porosity or any arches parameters. It's a relatively simple calculation, but of course there are many assumptions in the process, especially there are several assumptions in this equation, such as the transport numbers, as I said, the fact that we should not have any trace of hydrocarbons, no trace of shale. And all of these conditions may be compound because the exact transport numbers for sodium and chlorine are not necessarily the ones that are given to us in this formula or assumed in this formula, which are in laboratory conditions. So because of that, we don't expect a calculation that is equally as accurate as the one obtained with the resistivity logs. Okay, let's practice. Let me show you this example, and we're going to calculate our W for this example following the two paths. One, based on electrical resistivity measurements, and second, using spontaneous potential. The objective of this quick exercise is to show you the mechanics of the calculations based on the recipe that we just covered in the previous slide. First of all, it's important to recognize where we have shales, and based on that we have to draw the shale baseline. That's important. Then we recognize that the deflections of the SP log, which is the one shown here in red, are going to be negative, so we already know that we have higher sodium chloride concentration in formation water that we have in the mud. Obviously we have SP measurements in this example because we're dealing with a water-based mud. Also, we see that we observe that the deflection of the SP increases as we go down toward the water section of the well. And those deflections are increasing for two reasons. One is that the volumetric concentration of shale is decreasing as we go down, and that is indicated by the gamma ray log. So we have some decreased deflections because, especially at the top, because the volumetric concentration of shale is considerable. Second, we know that the upper formations are hydrocarbon saturated, and because of that we also have a decrease in the deflection of the SP log. So all of those things combine to produce the results that we see here. So what we have to do is we have to locate the water saturated section of the well, and we have to locate a section that has the favorable conditions for the calculation, which is minimization of presence of shale and also maximum deflection of the SP log, and we want to do this as far away as possible from the hydrocarbon zone. Okay, let me zoom into this plot. When we do that, these are the conditions that it appears that the depth at 5,700, somewhere 713, which is a local minimum here, is an ideal location. It's a water saturated sandstone, it has a local minimum, and it has the largest SP deflection. And I'm going to show you that at that point also we have an overlap of neutron and density logs, which is a desirable condition for indication and confirmation that we're in a clean sandstone. And the pink line here shows the estimated location of the shale baseline. All right, now if I increase the scale, here's how it looks. I have blown up the section of the well that is in the water saturated sandstone. What I'm showing here is that there are potentially two locations where we can take the readings of the SP log and make the calculations. At those locations we have overlap of neutron and density logs at both of them. Those are indicated by the pink lines. And the porosity that we read from the neutron and density logs is 33.5% sandstone porosity units. Now, those locations are chosen in the following way. We have a local minimum of the gamma ray log. That's important. We don't want to take readings where you have maxima of gamma ray log because we want to minimize the effect of shales. Second, we see that at those points we have the maximum deflection of the SP log, and those points are the farthest away that we have with respect to the location of the hydrocarbon zone. Both points have a deflection, a value of the SP of approximately minus 60 millivolts. With that, and knowing that the value of the shell baseline here is 0 millivolts, we take the difference between minus 60 and 0, and we calculate the SSP with its sign, which is minus 60 millivolts. To complete the calculations and to be able to compare them against the resistivity-based calculations, we take the reading of the deep sensing resistivity log at those points, and that reading is 0.43 ohm meters, as indicated here, because the deep sensing resistivity log is passing through the center in between two tick marks in logarithmic scale. Okay, so we take those values and we are going to do the calculations. So let's do the calculations. First of all, we go to the header of the well. We go to the header of the well, and we record what the resistivity of mud filtrate is and what the temperature was when acquiring that measurement. And that's the resistivity of mud filtrate. We also know what type of mud filtrate we have, and we assume that this is something that we need to confirm by experimental work, laboratory work, but in this calculation I'm going to make the assumption that the dominant cations and anions are sodium and chlorine. If I make that assumption, then I can use this equation right here, which is in the appendix, to calculate the corresponding equivalent concentration of sodium chloride in parts per million. So when you do that calculation, we find that we have approximately 12,880 parts per million of sodium chloride for the mud filtrate. This turns out to be a relatively fresh water-based mud. Second, now let's move on to calculate the RW. To do that, what we need to do is now to calculate the corresponding formation temperature at the place where we decided to read the SP and the resistivities. And that formation that value that we signal, that location, is 5,713. So we're going to take the surface temperature, or average surface temperature, which is 78. In reality, when we calculate this has to be an average temperature, not the one that was recorded here. But I'm going to make the assumption again that 78 degrees Fahrenheit in this example is a good representative number for average surface temperature. And I'm going to make the assumption that the KB, the zero depth for the logging, is precisely at the same point where the resistivity of mud filtrate was acquired. This is a very shallow offshore well, so that assumption is not so bad. And this is the total depth logger distance, which is 7,185 feet. The distance here that I have to write is 5,713, and this will be the bottom hole temperature, which we can read from the log here, the header, which is 140 degrees Fahrenheit, and this will be the surface temperature, which is 78 degrees. So if I do that calculation with those numbers, then I find that the formation temperature is 127 degrees Fahrenheit. Now, I go to the next one. I'm going to do the calculations based on the two methods, the resistivity and the SSP. So the formula for the SSP, that's Nernst's formula, I calculated, and then from the CMF that I calculated before, equivalent sodium chloride concentration, and this is a constant of 71, I solved this equation for CW, and I find that I have approximately 90,000 parts per million of sodium chloride equivalent. And then if I take the temperature that I have at that location, that's the formation temperature, I insert here and I insert this value in sodium chloride, then I find that SP tells me that the resistivity of formation water is approximately 0.049 ohm meters. Now let's go to resistivity measurements. As I said, we already know what the resistivity is, and we're going to solve this equation for RW. Porosity is what we calculated from the neutron and density logs. Saturation of water is 1 because we're in the water saturated zone. And for simplicity, I'm going to make the assumption that we have the easiest, most common values for Archie's parameter. This is not always the case, so we can expect differences. But if we assume these values, which are the normal values, then we end up with a resistivity of water, which is 0.048. And the difference is between the two values is in the third significant decimal figure. So, or second significant decimal figure. So that difference is very small in percent. And when the calculations are done this way, this is just confirmation that in effect this sandstone is clean. This is what the SP calculation can tell us, that based on the assumptions that we have a normal condition sandstone, that we can truly assume that that sandstone for that minimum value of gamma ray log that we took can be assumed clean, and that gives us a very good comparison with the RW. Of course, as I said, if M values of M or A would change in Archie's equation, we will get a different result. But we expect coincidence in the same order of magnitude. If I would have a factor of 2, a factor of 5, then things would not be able to reconcile, so we obviously had a problem. So the idea between which one is more preferred than the other, I would say if we have reliable neutron and density porosity logs, and we have reliable values of Archie's parameters, and all the environmental corrections are properly applied to the resistivity logs and the porosity logs, and also we complement the calculation of RW with a picket plot, in other words, more points, more likely the resistivity of water calculated in most cases will be more reliable from the resistivity logs than the SP logs, because of all the assumptions done in the SP logs. But that doesn't prevent us from doing the two calculations and comparing. And the difference between the two could signal and flag important properties about the rock that are making that difference to be large. For instance, very often when we have shaliness, presence of shale, could bias both, and because of that we could have also an indication that shale presence needs to be accounted for in the calculation of RW. Similarly with the calculation of porosity. So there are a number of things that could be reconciled. But just to emphasize, 100%, close to 100% of the time, if we have that opportunity, we will choose to calculate RW based on electrical resistivity measurements. And that concludes our presentation. So in summary, SP logs are extremely useful to calculate the electrical resistivity of formation water. Think about geohydrology. If you don't have access to neutron density porosity logs, then obviously this is an excellent way to calculate the resistivity of formation water, and then connect us in some way to estimate whether the quality of the water, how fresh the water is it drinkable or not. And as I said, it's better to, that calculation when you have the resistivity log is used for verification, corroboration, quality control. I mentioned that the SP logs originate from the electrolyte concentrations in between the mud filtrate and formation water and differential anion cation mobility. And SSP is a superposition of diffusion and membrane potential, two different origins, electrochemical origins for the SP potential. And SP logs are sensitive to shell concentration and hydrocarbon saturation. We also need to take into account bed thickness effect, invasion effects, anything that could bias the deflection of the SP for the calculation of RW. Now, we also have a few review questions. We have actually 3 pages of review questions. So I'm not going to go through all of them, but I'm going to take time so that you can all stop, pause your video, and look at these questions, which can potentially be used for pop quizzes, midterm exams, and the like. Going to part 2. Sensitive or not sensitive to invasion, presence or not presence of clay concentration. These are all matters that I discuss during the presentation. And I also discuss whether permeability is or is not indirectly assessed from spontaneous potential logs, petrophysical information, and the like. And with that, I would like to acknowledge my PhD student, great intelligent person, Joshua Bautista Anguiano, because many of the slides that I'm using here, I took them from his presentations that he's given at a number of places. His PhD dissertation is based on new laboratory measurements of spontaneous potential with intent to estimate hydrocarbon saturation. Great work that he's done. I also use some material from Schlumberger, especially the history of spontaneous potential log. I appreciate that Schlumberger allowed me to use those photographs, and Baker Hughes gave me a couple of slides, summary slides that I use in the presentation. So thank you, the three of them. Now we move on with the next topic. Thank you so much. Stay healthy, be happy, and enjoy this presentation. And by all means, let me know if you have questions, comments, and anything that comes to your mind. Thank you, and until the next one. And by the way, don't forget to look at your rocks. They're very important. Looking at rocks through the computer is not always as important as looking at rocks the way they are, looking at grain sizes, porosity, variability. Rocks are actually very complex and they deserve a lot of attention. So pay attention. Thank you. Hook and horns.